Good evening, everyone. My name is Paul Jibas. I'm a PhD student in biochemistry at Vienas University. Thank you for an opportunity to present our research. Today I'll be presenting a new method to analyze all genome DNA unmodifications and a machine learning approach to increase quality of the signal. To begin with, I want to say that I'm coming not from a special, but from different field of bioinformatics, because my group bases are chemists, and we are creating new methods to analyze biological objects, in this case, DNA modifications. And my job as bioinformatician is not to analyze signal in biological context, but to understand how it works, when it doesn't work. How can we improve quality of the signal? And our research topic is DNA modifications because it's important, it's dynamic, it defines cell fate, it's believed that it's the driving force behind human complex diseases. So, first of all, I would like to change your perception that not DNA modifications, but DNA unmodifications matter. 60 to 80% of human genome is modified, either MC, HMC, other modifications. Why should we invest resources into analyzing major part of the genome when we can analyze the rest 20%? And when we know which part is unmodified, we will know which part is modified. A simple example was in our class, if we want to tell a time, we can count the grains in the bigger part and tell the time, or we can count the grains in the smaller part, subtract this value from 1, and we will get the same result. So this is the logic behind our method TOP-seq. TOP-seq is DNA modification enrichment method. It has single CpG resolution, it's trans-specific, targets only unmodified CGs. Combination of all these features are specific to TOP-seq. There are also other methods like affinity-based methods, but they don't have CpG resolution. There are restriction enzyme-based methods, but they are restricted to their target sites. There's also whole genome bisulfite sequencing, which is a golden standard, but for it you need, it's expensive. You sequence all genome DNA, it generates large amount of data. So, what's TOP-seq? TOP-seq stands for tethered oligonucleotide prime sequencing. In this example, on the left, we have 2 genomic CpG sites. One is without modification, another is with modification. In this case, it's methylation. Our genetically engineered methyltransferase targets only unmodified sites and puts molecular tag to this unmodified CG. In result, we have genome-wide unmodified CGs with this molecular tag. At this step, we can add biotin and extract old region, or we can add small oligonucleotides that attach to this molecular tag, then add DNA polymerase that starts DNA sequencing from those oligonucleotides. This DNA polymerase is sequencing reads first. When we map those reads, we know where the 5' end is, so we exactly know which cytosine is unmodified, because from this cytosine the DNA synthesis started. We tested our method on model organism. It was bacteria with unmodified genome. So first of all, TOP-seq signal is accurate. In the first example, we have distance from mapped reads to cytosine. We can see that for most of the reads, distance is 0, so we are not randomly sequencing genome. It starts from CG sites. Second, it's reproducible. Correlation between technical replicates is relatively high at low coverage, and it increases when we increase coverage, and our signal is quantitative because we had unmodified genome, so we could introduce known levels of modification at wanted size. At this case, GC-GC. So GC-GC sites with high methylation have low coverage, with low methylation have high coverage. And control sites show constant coverage. It works in bacteria. We transferred our method to human genome and we faced some problems. We faced some problems because we had very low coverage, as we are trying to sell our method as a cheap one, as usable, and so we need low coverage, small library size, and this low coverage caused us variance. For example, we have two technical replicates. Even though coverage pattern is more or less the same, we have variance in coverage. So we solved these problems, like variance in coverage, undersampling, using kernel density. We calculated two densities, one for CG coverage, another one for CG density, and ratio between the two is so-called U density. This U density normalizes for CG content. It uses information from the neighboring CG sites. It normalizes for library size. Everything works perfectly. We published the thing in 2017, but there's still room for improvement. I don't want to call those things problems. Those are possible improvements, and those things are specific not only to TOPSeq, but all the enrichment-based methods. One of the problems is that TOPSeq has relative scale, because coverage can go from 0 to plus infinity, and it's very hard to say what's high coverage, what's high unmodification. Meanwhile, bisulfite has absolute scale, which goes from 0 to 1, and all from 0 to 100%. And it's easy to say what's high modification, what's medium modification. So we want to transform this relative scale to absolute scale. Another problem that we know from computational simulations is that different average methylation results in different coverage bias. And the third thing is genomic context bias. When we have different genomic elements, repeats, CpG islands, genes, they have different coverage. For example, SINE has high coverage, CG islands has low coverage, genes have variant coverage, but we don't know if this signal comes from GC content, mappability, base composition, so we want to somehow remove this bias. So our approach was machine learning. We constructed new neural network and tried to predict whole genome bisulfite signal using TOPSeq signal and genomic context. For genomic context, for each genomic CpG, we extracted information from 100 base pairs window. Some of the features were binary. If there's a sign repeat in the bin, is there a gene? Some of the features were quantitative, CG content, GC content, mappability, and we also extracted base that's flanking CG site, -3 +3 bases around the CG site. We used 2% of the genome CGs, trained our model, and evaluated it on totally different set that was generated in different laboratory. So this is visualization of our neural network. We have input layer, we have two hidden layers and output, and on the left side we have features with their importance. So the most important features are density and coverage. TOPSeq density and coverage makes sense because it's more or less, we are calculating methylation. So bisulfite is calculating methylation, we are calculating methylation. As other important features are those that carry information about CG content, CpG island, GC content, CG content. Then we have, interestingly, intergenic intergenic status is more important than genic status, then exon UTR, intergenic status is more important. Signs are here on top, and other repeats, line, LTR at the bottom. We don't know why signs are more important for this model. And the last thing is that when we select one nucleotide that's flanking the CG site, its importance is low, around 3%. The highest one is -2A, which means there is no adenine at second position. But when we sum up all those bases that surround our cytosine, it sums up to 40%. And it probably comes from the DNA methyltransferase binding or activity at the CG site. These are two scatter plots that show distribution between, on the x-axis, predicted values, on the y-axis, expected values for protein coding genes. So for the bisulfite that we use for training, but for other chromosomes we get correlation 0.9. For another bisulfite that we use for evaluation, we get correlation 0.85. In the end, here's a figure that shows correlation with our reference bisulfite. As I said, it's a golden standard. If we take row coverage, correlation is around 0.4, and neural network and estimate can reach correlation about 0.8. It's whole genome, single CpG resolution. And we can achieve this with 20 times less reads. We are still improving our model. We want to try it on mice. We want to optimize parameters. Now we are selecting 100 base pairs. Why 100? Maybe we can select more, maybe less. More predictive features. We want to try subcategories. Now we're taking science. Maybe we will take algo repeats and all other features. So thank you again for the opportunity to present research. This is my superheroes that supervise me, and this is our paper. Thank you.